Hello everyone. We have already discussed a moving coil galvanometer in the previous video, where we have seen that how a galvanometer works. We have also discussed the sensitivity of the galvanometer. Now, a galvanometer is a device which can measure small amount of current, and it can also give the direction of current. By the direction of current, we mean that if we are given a particular portion of a wire which belongs to a circuit, which belongs to a closed circuit, then there can be two directions of current, one in a particular direction, other in the opposite direction. So that direction can also be identified by using a galvanometer. So a moving coil galvanometer does two works. One is it measures the small amount of current, and secondly, it gives the direction of current also. So I hope that is already clear in the previous videos, where we have discussed exclusively the moving coil galvanometer. Now here we will discuss that how a moving coil galvanometer can be converted into an ammeter. Ammeter is a device which doesn't give the direction of current, but it only measures the value of the current. Now the value of current is much greater than as compared to the value of current which is measured by a galvanometer. So galvanometer measures current in microamperes, whereas ammeter measures currents in milliampere or even in amperes also. So let us see how we can convert a galvanometer into an ammeter. An ammeter is a device which is used to measure current through a circuit element. So let me show you the circuit element first. You see here a galvanometer having a resistance G is used. It is quite a higher resistance. The value of resistance of the galvanometer is shown by G, which allows a maximum current Ig to pass through it. If the current increases and if its value exceeds Ig, and if it passes through the galvanometer, then the coil of the galvanometer will burn out. So the maximum current which is allowed to pass through the galvanometer is Ig. Now suppose we have to measure a current I which is greater than Ig, because Ig is the maximum current which the galvanometer can measure. But we need to measure the current I which is greater than Ig. So what we do is we connect a very small resistance in parallel to the galvanometer, such that the extra current, which is I minus Ig, will move through the or will pass through the shunt resistance. This resistance is known as shunt resistance, and it is represented by S. So the galvanometer will allow only Ig current to pass through it. Now we know that the deflection in the galvanometer is in a linear scale, which actually is proportional to Ig. More is the value of Ig, more will be the deflection. Now we will see that I is also directly proportional to Ig. That means if Ig is represented by the deflection, then the scale can be graduated to represent I also, because Ig and I are directly proportional. That means if we increase I, then the deflection increases here, and we can measure it through the pointer. So only we have to change the graduations of the scale so that we can measure the value of I. Let me give you an example so that you will understand it more clearly. Suppose 10 ampere current is coming through this. We have to measure the maximum of 10 ampere current, but Ig is 2 ampere, that is 2 ampere can pass through it. So the rest 8 ampere will pass through the shunt resistance which is connected in parallel. So accordingly the galvanometer gives a deflection for 2 ampere, but it represents 10 ampere. Now let us take another condition in which let's say now the current is 5 ampere. So what happens is, now the current which passes through the galvanometer is half of the initial value, that is 1 ampere will pass through it, and the rest 4 ampere will pass through the shunt resistance. That means this galvanometer will now give the half deflection, which initially it was giving for 2 ampere. Now for the 1 ampere it will be half, and it will represent a current of 5 ampere. So I hope that it is very clear to you that the value of Ig changes in accordance with I. So instead of Ig, this will now represent I. So I hope this part is clear. This is the basic principle how an ammeter works. We have to connect a very small resistance known as shunt resistance in parallel to the galvanometer. To measure the large currents with it, a small resistance is connected in parallel with the galvanometer coil. The resistance connected in this way is called shunt resistance, that we have already discussed. Now see here, some terms we need to know. Capital G is the resistance of the galvanometer. Ig is the maximum current which is allowed through the galvanometer. 0 to I. I is the maximum value of current that the ammeter can measure. So the range of the ammeter will be from 0 to I amperes. S is the shunt resistance, very small resistance which is connected in parallel. And I minus Ig is the current which passes through the shunt resistance. Now, here we have the circuit diagram of the ammeter that you can see here. You can easily identify that Ig current passes through the galvanometer and I minus Ig passes through the shunt resistance, which is given by S. Now, you can easily see here the galvanometer and the shunt resistance, they are in parallel with each other. So, the potential drop across the galvanometer and the potential drop across the shunt resistance will be exactly the equal because they are in parallel with each other. So, if we use that condition which is written here, potential difference across the galvanometer is equal to potential difference across the shunt resistance. So, if that is the case, so the potential difference across the galvanometer is the current into resistance, which is Ig into G, is equal to the potential difference across the shunt resistance is I minus Ig, which is the current, into the resistance which is given by S. So from this equation we can find the value of the shunt resistance which is required for a range of current which is given by I. Suppose in the question if it is given the value of I and Ig, so I is the maximum range of the current, so the value of shunt resistance that will be required will be calculated by this formula, which is Ig upon I minus Ig into capital G, which is the resistance offered by the galvanometer. So I hope that this is clear to you. Now see here, by connecting a shunt of resistance S across the given galvanometer, we get an ammeter of desired range. You know, like the galvanometer and the shunt, the combined circuit, you can see here it is given by the dotted lines. This whole thing, that is the combination of the shunt and the galvanometer, is known as ammeter, right? Now in the ammeter we know that Ig into G, that is the voltage across the galvanometer, is equal to the voltage across the shunt resistance, that is Ig into G is equal to I minus Ig into S, since they are in parallel. Now if that is the condition, so we can find the value of Ig here. Ig is the maximum current which flows through the galvanometer, is given by S upon G plus S into I. You need to remember this formula, and one more thing you need to understand, that the value of S is much smaller as compared to the value of G, which is the resistance offered by the galvanometer. So the deflection in the galvanometer is proportional to Ig. This we have already discussed. I am just reading it out. The deflection in the galvanometer is proportional to Ig. That is, whatever deflection we get for the pointer which is used in the galvanometer, it is directly proportional to the current Ig, and hence it is directly proportional to I, because look at the equation here. Ig and I are directly proportional. If Ig increases, then I will also increase. That is, the current which passes through the galvanometer, if it increases, the current I will also increase. So you can see here they are directly proportional. So the current which passes through the galvanometer will be proportional to the actual current which enters the ammeter. Therefore, the scale which is used to measure the value of the current passing through the galvanometer can be used to measure the total current which enters the ammeter directly. I hope this is clear to you. Now, if we want to find the total resistance of the galvanometer, then ammeter, total resistance of the ammeter, then these two are in parallel. So if they are in parallel, then we know that the equivalent resistance is the reciprocal of 1 by S plus 1 by G. So if you take the reciprocal, then GS upon G plus S. This is the total resistance or effective resistance of the ammeter. Now you can see here, always you remember one thing, that when resistances are connected in parallel, then the equivalent resistance will be smaller than both of them. That means out of these two, shunt is the smaller one, so the equivalent will be even smaller than the shunt resistance. That means what we can conclude here, the whole ammeter is a low resistance device. It is a low resistance device. Now, the shunt, if we want to define shunt, it is a low resistance. It is a low resistance which is connected in parallel with a galvanometer to protect it from the strong current. Some of the uses of the shunt resistance are: it prevents a galvanometer from getting damaged due to large current, it converts a galvanometer into ammeter, and it increases the range of the ammeter. I hope this is clear. Now, some of the key points of the galvanometer which you need to know is: first is, since an ammeter is a parallel combination of the galvanometer and the shunt resistance, so its resistance is even less than that of the shunt resistance. So the effective resistance of the ammeter is much less than the resistance of the galvanometer if we compare it with the galvanometer. So it is a very low resistance device. The next is, because of its very small resistance, an ammeter is placed in series circuit and does not practically change the current in the circuit to be measured. Always remember that ammeter is placed in series with the circuit, and since it is having a very low resistance, so it will not affect the total resistance of the circuit. Very negligible effect is there. Okay. And in ideal condition, an ammeter has zero resistance. So a resistance of an ideal ammeter is zero. Okay. Now, higher the range of the ammeter, we can increase the range of the ammeter by decreasing the value of the shunt resistance. So all the excess current passes through the shunt resistance. Higher is the range of the ammeter to be prepared from a given galvanometer, lower is the value of the shunt resistance required for the purpose. I hope this is also clear to you. The ammeter of low range has a higher resistance than the ammeter of the higher range. Obviously this will happen because if we increase the range, the value of the shunt resistance decreases. So the resistance also decreases, equivalent resistance. Now the formula for shunt resistance we know is given by this. Now the value of I is greater than Ig, and we can increase the range. I is the maximum value of current which is measured by the ammeter. Now we can increase the range, we can increase the value of I from Ig. The value of S remains positive, but we cannot decrease the value of I, because if we decrease, then this term becomes negative. That means the shunt resistance becomes negative, which is not possible. A resistance cannot be negative. So what we can say is, we can increase the range of the ammeter, but we cannot decrease the range. So the last point we will discuss here, the range of an ammeter can be increased, but it can never be decreased. I hope the whole thing is very clear to you, but still then if you find any doubt, you can post me that.